We know how to multiply fractions. What about dividing? Let's pick on an example that's going to give us a little bit more work to do. How about, yeah, let's do, I don't really like any of these. Let's do part C again. So negative 14 divided by 3/2. So what's our strategy going to be?
Is this the one you do the keep, change, flip?
Yeah, so tell me about keep, change, flip, because this is a common refrain coming to dividing fractions. So what are those three? I'm going to write those down. Keep, change, flip. What are those three things telling us to do?
You keep the first fraction and then you change the division into multiplication.
Okay. And?
Then you flip the next fraction.
Okay, great. Keep, change, flip. Okay. So we're going to keep that first number here, negative 14. Call that the dividend of the division problem. We're going to keep that as it is. Don't touch it. We're going to change out division for multiplication. So we're reversing the operation here. We're turning it from a division problem into a multiplication problem. And the good news about that is that we know how to multiply fractions based on what we said a minute ago. Right? And so this is taking us from an unfamiliar problem type into a familiar problem type. But it comes at a cost. We can't just change an operation for its reverse without also doing something to balance that to keep it so that the answer is still the same as it was in the beginning. When I change division for multiplication, I also change the divisor for what? For its flipped version, which is often called the reciprocal. So right, using mathematical language around it. To find the reciprocal of a fraction, we just interchange numerator with denominator. So instead of 3/2, we end up with 2/3. And that's all there is for division. As soon as we turn a division problem into multiplication instead, now we know what to do. And what is that? Multiply across, except that we need this first thing to be a fraction. So how do I make negative 14 into a fraction? Over 1. Okay. And what should I do with that negative sign? Yeah, let's put it upstairs on the 14, just like we did in the last example. And now I can just multiply straight across. New denominator is 3. New numerator is negative 28. Lowest terms? Yeah, again, here's this 28 showing up at us again, right? Only 4 and 7, and by extension 2, go into that. And 3, nothing else goes into 3 besides 3 and 1. 3 is already prime. So there's no overlap in the common factors of those two things, and so that's our answer. So that's all there is to division of fractions. Turn it immediately into a multiplication problem, and from there, you know what to do. Just multiply straight across. Step that we didn't have to do before, but now is helpful. Right? It can help us to reduce this fraction 180 over 9 into lower terms. Because we find that when we look at those numbers which go into 180, I'm just going to quickly break out the prime factorization of this. Divide it by 2 until we get down to 45, then divide it by 3. 15 also has a 3 in it, 5. So 180 actually has a lot of prime factors. Right? It's got 2 from up here. It's got a pair of 2s, it has a pair of 3s, and it has a 5. Right? So there's a lot going on for 180. Meanwhile, 9, what does it have? It just has a pair of 3s. But it turns out that these two can agree on something. These two numbers can agree on not only one factor of 3 in common, but in fact 2 factors of 3 in common. And so now that we know that, how do we actually reduce a fraction? This is the conversation we haven't had to have yet until now. Once I know that 3 is a common factor of both of these fractions, how do I use that to get lower terms? What do I do with 180 and with 9? In other words, where did your 20 come from that you got for your final answer? Yeah.
You divide each by 9.
Divide each by 9, exactly, right. So one of the things that's built into the DNA of how fractions work is that because every fraction is a division problem, if I multiply or if I divide both the numerator and the denominator by the same quantity, I'm gonna get the same quantity out at the end, right? My new fraction is gonna have the same value that my old fraction did. So 180 divided by 3 is gonna give me 60. 9 divided by 3 is gonna give me 3. And this new fraction, 60 over 3, has the same value that the old fraction, 180 over 9, did, because I divided both numerator and denominator by the same quantity. And yet again, we can play the same game with 60 over 3. We can observe that they both have a 3 that they can agree upon. We can do it one more time, and thereby arrive at not really 20, but 20 over 1. But 20 over 1, because of what we know about fractions with 1 in their denominator, we can rewrite that as a whole number. In the reverse way of when we convert a whole number into a fraction, we can convert that fraction into a whole number 20.